So I just would like to give again a brief overview where we are. And let me share that screen there. Okay, so I think you can see that now. So again, we are in that StatMag blog, and so I'm giving these first two lectures now. Last week we talked about, we started from basically from the truth, right? From the very beginning, the Schrödinger equation that governs everything more or less in our field, right? And then we introduced sort of approximations to it, Born-Oppenheimer approximation, and then the classical motion of the nuclei, and then we talked about molecular dynamics, and then we discussed time-stepping algorithms, and today I would like to take this further, and I hope I can explain how we can use our workhorse in electronic structure theory, density function theory, to use that, what you have heard in lectures that were given before me, sort of to combine this with molecular dynamics to something that's called Born-Oppenheimer molecular dynamics. Yeah, so that's we're going to do this, and one of the essential ingredients for doing molecular dynamics is to calculate forces on the nuclei, and so we're gonna learn about one theorem that allows us to do this very efficiently, and that's the Hellman-Feynman theorem. And we also prove it. We can prove it because you can prove it in just a few short lines. And then I will talk later today about ensembles and thermostats, because at the end of the day, you would like to do molecular dynamic simulations to calculate some observables, right? So that's usually what you're interested in if you're simulating a dye-sensitized solar cell, or if you simulate an interface between semiconductors or something like that, or if you do machine learning, obviously you always want to calculate some properties, and typically the system that you're looking at is at room temperature, or at a finite temperature. At least can be a low temperature, but typically not at 0 Kelvin, right? So then the question is how you introduce the concept of temperature at all. What is actual temperature, and how do you introduce it, and how do you control temperature in molecular dynamic simulation? So that will be this point here, and I will not talk much about property calculation. So that's the program for today. And then last time I basically gave a very short, brief overview of the next couple of lectures here. So let me switch slide again. To the is it this one? I think it's no. Okay. It's this one. Yeah. Okay, so so if I sort of summarize sort of in more sort of mathematical terms, what we have done is that we have looked at the full coupled electron nuclear Schrödinger equation, and we have introduced the Born-Oppenheimer approximation. So there were two approximations there. One was that we only consider the electronic ground state. And the second one was that we took advantage of the fact that the mass of all the nuclei is much larger than the mass of the electron. And so we could then go from the fully coupled electronuclear Schrödinger equation into something that was much simpler, which was just a Schrödinger equation for the nuclear wave function, okay, phi of r. And all the electronic degrees of freedom, there's inside that potential energy surface here. And these potential energy surfaces, this is what you can calculate with electronic structure codes for a given nuclear configuration vector R, okay? And this would then just be the kinetic energy operator for the nuclei. So this is a simplification, but this equation you can still solve only maybe for 5 to 10 degrees of freedom, so very small systems. And so the next approximation was then the classical approximation of the nuclear motion. So that's valid at high temperature and for high masses of the nuclei. And essentially what you do here is you're replacing the time-dependent Schrödinger equation by Newton's equation of motion, right? And that's and we have seen how one can do that last time. And that's a major drastic simplification, because instead of the nuclear wave function here, right? You just have the positions of your nuclei. They are now point particles, and they just accelerate in time according to force divided by mass, right? So that's the major simplification. But it's not that simple, because the forces here on a given nucleus, they depend on the configuration of all the other atoms in the system, right? So that means that so you have one of these differential equations for each nucleus, and they all coupled with one another because the forces, they depend on all the positions of all the nuclei in your system, okay? So that means, even though this equation is much simpler than that one, you still need, you cannot solve it analytically, and you have to, you have to solve it numerically. And this can be done. It's just a, a system of linear second order differential equations. And we have looked at some of these algorithms, how you can solve them. So 3 of them, Verlet, velocity Verlet, and leapfrog. The leapfrog we didn't discuss in detail last time. Okay, and solving these Newton's equation of motion for a collection of your atoms that can be constitute molecules or material or whatever, is referred to as molecular dynamics simulation. Okay, there are any questions on this? If you have any, just interrupt me, and I'm happy to explain it to you, of course, if I can. Okay, so that's this. Okay, so now I would like to sort of explain how we do molecular dynamics using density, using electronic structure theory to calculate the forces. And remember, in molecular dynamics, all what you do, you move your nuclei from one position r of t to another position at an increment in time t plus delta t. Yeah. And in order to make this move, so you need obviously the force acting on the atoms. And if you use electronic structure theory, how do we get the force? Well, maybe I can ask you, so how do we get the force for this from electronic structure theory? Do you have any idea?
Well, it would be taking equation 5 from the slide.
Yes, if you can describe that equation in your own words.
So that's the expected value of the Hamiltonian at the ground state.
Yeah, expected of the value of the ground state. So It's a ground state because you minimize, right, the expectation value here of all the antisymmetric wave function, electronic wave functions, right? And at that minimum, that wave function is psi 0 r prime, right? And that's then the ground state energy. And the electronic Hamiltonian has all the terms, right? Kinetic, electron-nuclei, electron-electron, and nuclei-nuclei. And this minimization problem, well, is equivalent to actually solving, you know, the eigenvalue equation for the electronic Schrödinger equation, right? H E psi r0 is equal E r0 psi r0. Okay, so you need the energy for that, and then for the force you need the derivative of that energy with respect to the nuclear coordinates, and this is this here, yeah. So you have to calculate then the ground state energy at different nuclear positions, at different displacements, okay, and then take the gradient, yeah. Take the gradient then at your instantaneous position r. So this is a lot of work because you know, in order to have these calculate this gradient, you have to do, you know, you don't know it analytically in the end, at least at the beginning. So you would need to do lots of finite difference calculations to numerically estimate that gradient. Yeah, and that would take a lot of time. So just for a single atom, basically, if you do forward, backward in each direction, that would require you to calculate 9 single point calculations just to get the force. Okay. So there is one theorem that is extremely useful that that we can use to avoid these numerical calculation of the gradients. And that's this Hellman-Feynman theorem that I would like to discuss in some detail. So it's all about calculating, you know, like these kind of derivatives efficiently. And in order to sort of show that or introduce that theorem, I sort of show this in a little bit in a more general fashion. Sort of what I consider is a general Hamiltonian H. Doesn't have to be an electronic Hamilton, can be anything. That depends on a parameter lambda, okay? And H is a function of lambda. And then you consider an eigenfunction of this Hamiltonian, okay? So which we call psi lambda. And this eigenfunction doesn't necessarily have to be a ground state. You know, it can even be an excited state, and that, you know, like then the theorem still works. And the corresponding eigenvalue to that wave function is E lambda. Okay, so the only condition is that these two are eigenvalues and eigenfunctions of H lambda. Okay, now what does the Hellman-Feynman theorem state? It states that you take the expectation value of H lambda, okay, in that eigenstate. And you take then the derivative of that expectation value with respect to lambda, okay? So if you look at this, I mean, it looks very similar to actually to the force expression, right, that we need to calculate if you identify lambda with your nuclear position, yeah? Or with an x coordinate of your nuclear position, yeah? Now the theorem states that this derivative is actually equal to the right-hand side expression. The right-hand side expression basically is just the derivative of the Hamiltonian with respect to lambda, and the expectation value of, basically the expectation value of that gradient. Yeah. So first of all, the question to you, are you surprised that this is true?
I mean, I saw the demonstration in the following slide from the material, so.
All right, okay, so you have already read it, okay.
Yeah.
So has anyone not read it? Okay, so you all know that, so that's good. It was a little test whether you have actually looked at the notes before. So that's a consequence, just a consequence of the fact that the Hamiltonian is actually a Hermitian, right? So here's the proof. So if you have something like this, then you have to apply the chain rule, right? Because all of these, the wave function and the Hamiltonian is dependent on lambda. So you have to apply the chain rule. So you have three functions here that depend on lambda. So therefore you have three terms: derivative of the wave function with respect to lambda here in the bra and the cat, and also the derivative of the Hamiltonian, of course. Okay. Now, so this one, the first one is quite easy because you know, we know that this is an eigenfunction of the Hamiltonian, an eigenvalue e lambda, so that we can pull out of that bracket. But now this second term is maybe not as straightforward because the Hamiltonian acts on a derivative of that wave function. But here you can just do the usual trick, right? That you say that the Hamiltonian is Hermitian, so you can just move the Hamiltonian into the bra vector. Okay. And then this is again an eigenfunction, so you can take E lambda star out of that out of the brackets, since E star is equal E, so nothing changes. And then you got rid of that Hamiltonian, and then what you're left with is psi lambda times dd lambda psi lambda. Okay, so that's the second one, and the third one is unmodified. Now, if you look at the first two, you can see that this is actually can be written as the derivative of the norm of that wave function. Yeah. Again, chain rule. So then, if you apply the chain rule to this, you get that. And since we're always dealing with normalized wave functions, and these wave functions have a norm of 1 independent on lambda, the norm doesn't depend on lambda, therefore the derivative is 0, okay, of this. So what you're left with is then just the third term, and therefore you have proven that Hellman-Feynman theorem. Okay, are there any questions on this? No, so you say it's very powerful and very general because you have not assumed any particular form of that Hamiltonian. You have only used the fact that the Hamiltonian is Hermitian, and every sort of proper Hamiltonian, and at least in undergraduate quantum mechanics, is Hermitian. Okay, so that means that this theorem is valid for instance, you know, like the electronic Hamiltonians that you have in Hartree-Fock theory, or it's valid also in Kohn-Sham theory in DFT, right? The only condition is again that psi lambda is an exact eigenfunction of that Hamiltonian. All right. So now I would like to sort of go. Oh, sorry for that. I would like to. Sorry for that. Would like to go back to. Well, first I would like to go back to my slide. Do you see my slide still?
Yeah, we're seeing your screen.
Resume share. Resume share. Sorry. Yeah, my laptop is too smart. It sort of knows that I get a call and all kinds of things. So I would like to go back to Kohn-Sham density function theory because would like to then show the expression how we can calculate the forces that we then need for molecular dynamics from DFT. Okay, so you have probably heard this already once or twice before. Now, maybe now you hear it a third time, probably always in a slightly different way and notation. But that's good to hear it in sort of several different ways. Now, in quantum density function theory, we know that the quantity of interest is no longer the wave function, but the density, because the density basically determines where your nuclei are, the position of your nuclei. The position of your nuclei and the number of electrons determines your Hamiltonian, and the Hamiltonian determines the wave function, right? So these are the correspondences in the end. So okay, so the density, and then in quantum density function theory, you do introduce again orbitals, but just one electron orbitals. So the squared sum of those is then the density. You go through all these Hornberg-Quantum theorems and quantum theory, and at the end of the day, what you have is an expression like this that you have to minimize, right? So this is the density functional expression where you have the kinetic energy of this non-interacting reference system that's formed of these quantum orbitals, right? Then here you have the interaction of the density with the electrostatic potential due to the nuclei. Here you have the electronic repulsion energy, right, between the electrons. So this is exact. And then you have all these sort of quantum mechanical effects of electron correlation and exchange between the electrons. So you all put this in the exchange correlation functional. It also includes the difference between the exact kinetic energy and this kinetic energy that you have there, and then this trivial constant between the nuclear cores. So this is quantum theory, and you need to minimize this expression with respect to all the densities that integrate to your number of electrons n, right? And if you then also assume that these orbitals should remain orthonormal, which is done here, then you get these quantum equations. This is then a set of eigenvalue equations that you need to solve for these orbitals phi, right? And again, sum of phi I squared gives you the density. Okay, so you still remember all of that? Yes. Okay. So again, here, like Hartree-Fock, the DFT is a self-consistent field equation because the quantum Hamiltonian already, in order to construct the quantum Hamiltonian, you need already orbitals, right? You already need the solution. So that means that you have to guess the solution first, construct your quantum Hamiltonian here in this way, and then diagonalize it to see whether the output orbital matches the input orbital. Usually that's not the case, and then you have to sort of reiterate, until input orbitals are output orbitals, right? Okay, so that gives you then the ground state density. It's not the exact ground state density, and it's not the exact ground state energy. Why is it not exact? Anyone?
Because of the change energy that we are approximating it.
Yes, yes, exchange energy is, but the exchange energy itself is actually very clearly defined. It's defined in Hartree-Fock theory, right? But basically, the exchange energy sort of is very well defined for a set of orbitals, but the exchange energy is not all of the non-Coulombic electron-electron interaction energy, right? That's the thing. So you have this very complicated electron-electron interaction energy, right? So this is this VEE, so all the Coulomb interaction between the electrons. And so the easiest, then you can break this down in these different contributions into the Coulomb contribution, which is just this one there. this one here, and this is the classical thing. That's also what you have in classical electrostatics, right? And that's correct. And then you can, and then we know that there is something that's also called exchange energy. But Coulomb and exchange energy, those two together, they're not giving you the full electron-electron interaction energy, because if it would be the case, then Hartree-Fock would be exact, right? But what is Hartree-Fock missing? Hartree-Fock is missing electron correlation, right? Because it's a single determinant, and electron correlation you only get if you have more than one determinant. So in the end, what you have here in this exchange correlation functional is a functional expression of the exchange energy in terms of the density and of the correlation energy. And so the exact expression of this exchange correlation functional is unknown and sort of has kept basically maybe 2 or 3 generations of theoretical chemists busy to find suitable expressions for that. But it's so this is where the where all the approximations are coming from, and this is why you have hundreds of functionals in the literature. Maybe only 10 are used, but all of these have aimed to approximate an exchange correlation functional. Okay. So if you had the correct exchange correlation functional, you would also get the exact ground state energy. But that's unfortunately not the case. But depending on the system, we have very good approximations to the exchange correlation functional available. All right. Are there any questions on this? Further questions? No. Okay. Just ask. Okay. So solving this quantum equation gives us the total energy, the orbital energies, the quantum orbitals, and then due to equation, what is it? I can't see, equation 14, and the density. Okay. Now the question is, how can we get from that then the forces? And well, we just have to do what we have done before. Now we have these energy expression from the quantum theory, right? So you take all your quantum Hamiltonian, and you take your quantum orbitals, you make, let's say, a determinant out of that, and then you calculate that expectation value, and that gives you the energy, the DFT energy, and then we have to calculate the gradient with respect to the nuclear coordinates, okay, to get the force that we then use to propagate the nuclei in molecular dynamics. And as I said before, so we can use the Hellman-Feynman theorem to do that, and can basically drag that derivative inside that expectation value. And what we just then do is we calculate then, we basically numerically differentiate the quantum Hamiltonian with respect to the nuclear coordinates. So you can do that. It's very easy. You just do this, so you can sort of analytically do that. And there's no need to recalculate any quantum orbitals or something like that. You just take the quantum orbitals that you obtain from the energy minimization, and to calculate then the expectation value of the gradient. Okay. So that's really an advantage, because you don't need to calculate, let's say, nuclear derivatives of the wave function, right? So this is very tricky and difficult to do. So you don't have to do that to get the force. Okay. So if you then do that, derive the nuclear forces from this equation, and you stick then these forces into, let's say, velocity VLA or VLA algorithm to propagate your nuclei. Then you call this scheme a density function theory-based molecular dynamics, or a DFT-MD, or some people call it ab initio molecular dynamics, right? So that's, and you call it this way because you calculate the gradients from electronic structure rather than from, let's say, a parameterized force field or something like this, okay? Often then parameterized force field actually are parameterized to these kind of electronic structure calculations, okay? Any questions on this?
Yeah, are there any public package that already has these implemented? Like,
yes, that's a very good question, and I actually have. Let me try whether I can sort of share again the share the screen again. Can you see that? Probably not.
yeah, we're seeing your browser, I think.
Oh, you're seeing my browser. Okay, that's good. So this is, for instance, a package that I'm using in my research group. You know, there are lots of well, not lots. I mean, there are probably lots, but there are probably a few rather common packages that would do, like, let's say, efficiently ab initio molecular dynamics to the way that it's sort of efficient enough that you can do real research and can publish papers, for instance. Yeah, and it's not so easy to do that efficiently. So one of these packages that is also used, let's say, a lot in the UK, at UCL, Imperial, is the CP2K package. And so you can see the functionalities of this. So it's a quantum chemistry and solid state physics software package, can perform atomistic simulations, solid state, molecular, periodic, material, crystal, biological systems. And so what this program is doing is that it solves, so usually the first step, I mean, it can do many things, but now in the ab initio MD context, it solves the, for each MD time step, it solves the Kohn-Sham equations, right? It gets the ground state density and the Kohn-Sham orbitals, all right? And also the forces using the Hellman-Feynman theorem that we just discussed, okay? And then it just actually, and then what is implemented in that code is the velocity Verlet algorithm for the propagation, and it's using the velocity Verlet then to propagate the nuclei. And you can see here the details. I mean, now it's where it gets interesting. Obviously, you don't want to wait hours or something for a 200 atom system to make one time step. So you have to, you have to be. So these are packages that have maybe 1 million lines of code, highly optimized, so that that you can really do something with them. And so this particular package, for instance, is using Gaussian basis set and plane wave basis set to expand the orbitals and solve the Kohn-Sham equations. So it uses Gaussians for the exchange part. You do a real space integration there. For the electrostatics, which is a long range interaction, it uses a plane wave basis set to calculate the electrostatic interaction. So these the Coulomb integral rho r times rho r prime over r12, right? So that's done in that code in a plane wave basis set. And so you also see basically, like the kind of functionals that are available, exchange, and that refers to this EXC, like exchange correlation functional. You have LDA, local density approximation, GGA, generalized gradient approximation. You have heard of this in the DFT lecture, I'm sure. But beyond that, it can do more even. It can do wave function theory, so perturbation theory, MP2, so that's Hartree-Fock plus a perturbation energy, random phase approximation. It can also do semi-empirical, right, which is much orders of magnitude faster, but maybe not as accurate. And in addition to ab initio molecular dynamics, it can also do classical molecular dynamics. I talked about this last time already. So it has implemented a couple of usual classical force fields that you usually use to simulate proteins, DNA, or organic semiconductors, things like this, like amber or charm. And so here it has a lot of, let's say, potential energies available, like sort of DFT, ab initio, and as well as classical force fields. And it can also do lots of kind of different kinds of dynamics, right? So what we have discussed until now was just solving Newton's equation of motion and doing molecular dynamics on the ground state potential energy surface. But like to accelerate time, to access longer time scales to sample, let's say, rare events, you have to add sort of, you have to do some kind of different tricks to accelerate things. And this you do with advanced sampling methods like metadynamics, for instance. So I think people will talk about this sort of in the next month. Then you can do excited state dynamics. So that would be of interest for when you do sort of dye-sensitized solar cells or excited state dynamics. So then that would be ENFest. We are not, I don't think we discussed this in this lecture course. So that's beyond Born-Oppenheimer. And yeah, you can do, calculate transition states, get rate constants for chemical reactions, all these kind of things. So yeah, have a look at this website. I mean, there are also other codes, obviously. I'm a little bit biased towards this one, but I'm sure Gaussian can also do some MD, but not very efficient, I would say. So there is NWChem. I mean, there are lots of different packages, but typically it's only one or two or three that are, like sort of highly optimized towards, very good at one particular task. And CBDK is very good at doing ab initio molecular dynamics. Okay, now enough advertisement. So what I just would like to show you a movie. Quite sure how to do that. Here. Okay, so I hope you see this here. So last time I showed you this, and this is, sort of a very nice sort of example of a sort of simulating something that has to do with, sort of renewable energy generation, things like this. So, so there is an interest to, to convert sunlight into some chemical energy or something. And very often you do this with, or sort of one promising way to do this is with transition metal oxides in contact with liquid water. And sort of one of these systems that are very interesting, so basically that many experimentalists look at is, for instance, sort of cheap oxides like hematite, iron oxide that you see here. And so the, the question is, do we understand sort of basic properties, let's say, of interfaces between oxide materials and liquid water? And so why is this of interest? It's of interest because we would like to understand what's going on at these interfaces. And if you just do experiments, for instance, you have this sort of macroscopic observable, but you don't really know exactly, actually, like how your where your atoms are, the stoichiometry of your surface, and sort of what's going on in an atomistic picture. And this is where these ab initio molecular dynamics can be useful, sort of to understand what's going on, or what the what, let's say, surface stable surface terminations are, or how the dynamics looks like, or for instance how chemical reactions occur at these interfaces. And so here's just okay. So here's just a movie of ab initio molecular dynamics simulation, and it's quite a short movie. So this is, as you can see here, are the water molecules. Here's the hematite that is terminated here with an OH bond. And so what's done here in that movie is exactly what we have discussed, using actually that CP2K code that I've just advertised. In this case, you are using a density functional that is quite expensive, because hematite forms antiferromagnetic layers. So basically, like this layer here that you see, the top layer, each iron has 5 spins up, and then the next layer, each iron has 5 spins down. And you cannot treat this properly with GGA functionals, for instance, or with LDA. So you have to use hybrid functionals, and I'm pretty sure that you have heard about hybrid. I assume you have heard about hybrid density functionals, right? Have you? I guess.
Yeah.
Yeah. So they are quite expensive to use in ab initio molecular dynamics schemes. And so this is an MD trajectory where you employ these. And again, here at each time step, again, you solve Kohn-Sham equation, and you get the forces with which you then move your nuclei. So that's an MD trajectory at around 300 Kelvin. Okay. So the only thing that you see here on that time scale that is shown here is the dynamics of hydrogen bond formation and breakage of these hydrogen bonds. Okay, but there is no, on that time scale, there are no chemical reactions that you can see. But what you can typically see is that, for instance, you can calculate now what we are doing now with machine learning methods is that you can actually sort of fit the machine learning potential to these kind of reference calculations, and then do MD simulation on much longer time scales, where you then be able to calculate the dynamical quantities, diffusion coefficients, mean resonance time, these kind of things. Okay, and later on, then maybe even how essentially a hole that you create, electron hole that you create in the semiconductor, how that leads then to the oxidation of a water molecule and the formation of molecular oxygen. Okay, are there any questions on this? No.
I have a question. How big are these simulations in terms of how many molecules are there?
Yeah, so so you have about 2,000 electrons in this system. So the cost of these always depends on the number of electrons that you have. So that means you have typically 100 water molecules and couple of layers of this hematite, probably a couple of hundred hematite atoms. Now you're using pseudopotentials. I don't know whether you have heard about pseudopotentials. So you're not solving the Kohn-Sham equations for all of the electrons of an oxygen or of an iron. That would be completely out of question to do that. So you only, so this is why you have pseudopotentials, right? So for iron, for instance, you treat all the electrons with a pseudopotential except the valence electrons, the 3D electron. So you still then have 16 and sort of, sorry, it's a semi-core. So you also have the 3p electrons and the 3s. So it's a 16 electron pseudopotential in the end. So each iron has 16 electrons explicitly treated. And iron is 55 in the periodic table. So the rest of the electrons are treated with a pseudopotential.
Okay.
Yeah, that's a good question. And that was pretty much actually what we could afford. I mean, these calculations we did in 2016. So this on the national supercomputer in the end, you cannot do this anywhere else. And at that time it was maybe 2,000 electrons, and probably it's not much more these days. Maybe it can go up to 3,000 in the end. I mean, it's obvious you can also do 100,000 if you like. I think the question is what what you want to be after. If you just want to do a single point calculation, then you probably can go to many thousands of electrons, right? But if you want to do MD simulation, where each picosecond takes 10,000, needs 10,000 single point calculations, then then it gets very expensive very quickly, and then you have to sort of can only do this for sort of relatively small systems. Okay. So yeah, that's also a good thing. What are actually the time steps? What are actually the time steps? So can I ask one of you, what do you think what actually the time steps are in these molecular dynamic simulations? We didn't talk much about this. I mean, we just had this, like this delta T, where basically you propagate the nuclei back by one time step by delta T. Everyone would like to make a guess how this, on which time scales these delta T's are. Are you still with me? Ah, yes, there are 7 people.
Yeah, but I mean, I assume
there's no. There's just have a guess. What
yeah, I mean, I assume the time step should be higher than a classical DFT, but smaller than classical molecular dynamics.
Yes, that's a good way of thinking. So it's sort of comparable to a classical MD time step. But what is a classical MD time step?
And I'm not familiar with the order of magnitude.
Is anyone actually doing MD simulation?
I mean, I have in the past, but I don't remember the
no. Is anyone doing an MD simulation in the project? Okay, so I mean, okay, so if we don't, if we have another feelings, then maybe we should basically then think, I mean, on which time scales actually do you have molecular vibrations? Like molecules that vibrate, right? I even have this very simple picture there. This one, right? So one such a vibration, on which time scale is this happening?
I have no idea.
Anyone? I give you 3. So it's let's say seconds.
No, it's
microseconds or
picoseconds.
Microseconds or femtoseconds.
I don't know if you're seeing the chat.
Oh, sorry.
Yeah, but some people have answered
chats.
femtoseconds.
Nanoseconds, several femtoseconds per step. Okay, well, that's very good. Well done. So it's indeed femtoseconds. Yeah, so well done, Juan Yu and Chayavat. You can just I have the vibrational frequency in centimeters, right? 3,500 centimeters. Now you can insert this into the you can convert this into frequency, And then you discover that basically the stretch motion of a water molecule is roughly 8 to 10 femtoseconds. Okay, so in 8 to 10 femtoseconds, you have one oscillation. Now, during the MD simulation, you obviously would like to represent this oscillation, right? So you want to have, if you have a sine, you want to basically, and you know that the period of the sine is 10 femtoseconds, and you want to represent that sine, then you need a couple of points, right? To represent the sine motion as basically the plus and the minus of the vibration. Okay, so typically, you know, you say, okay, so how many points do I need for an oscillation? Maybe 10 is good. Okay, 10 maybe. Okay, so if the vibration is 10 femtoseconds, then that means that maybe my time step should be 1 femtosecond. And, you know, then I should be able to represent everything. And that's actually the case. So if you do classical MD simulation, like this one, for instance, there, okay, like this is another one. This is actually a protein. You know, like I've shown this before with an oxygen molecule trying to find the active site. Then, well, actually, this is a bad example. Let's go back. Let's go back to this one there. Then you would choose a femtosecond, right? So here, since you do in classical MD simulation, you would actually choose a femtosecond, yeah, for let's say hydrogen bonded system, and the hydrogen is allowed to vibrate. Now, when you do ab initio MD, then you choose a little bit of a smaller time step, because in ab initio MD you have to outweigh the larger the time step, the more you step, the more you have to reconverge the wave function. It takes a lot of time. So therefore, you choose a little bit of a smaller time step than the reoptimization of the Kohn-Sham equation wave function. The new step then is probably a little bit faster, but then you step a little bit less in time. So there is a sort of something to, you know, things to optimize. And usually, so in this simulation, for instance, you took 0.5 femtosecond as a time step. So that's what's typically chosen in ab initio MD of hydrogen bonded system, 0.5 femtoseconds. So now, how many time steps and how many Kohn-Sham equations do you have to solve to simulate 1 picosecond? Well, that would be 20,000, right? So you need to do 20,000 electronic structure calculation to simulate 1 picosecond. And that's, you know, this is why you can only run these things on the biggest machines. That's the reason for this. Okay. And nanosecond would be out of the question, because then it would be, you know, it would require you to solve 10 million Kohn-Sham equations for 10 million different positions. Each one takes maybe, you know, a minute, and then, you know, you wait many years or hundreds of years. So so therefore now, you know, like in the later part, in the later part of this section, you will come across machine learning methods that can use basically then these kind of information, and for instance, to generate the neural network potential that then allows you to access much longer timescales, right? With a hope to not to lose too much accuracy. Okay, and so that's the. So another thing that that ab initio MD allows you to do is chemical reactions. I don't know how interested you are in how much of a chemist you are, but I was always fascinated in, you know, like bomb breakage of bombs and formation of bombs, and so this is actually a simulation that I did when I was a postdoc in the end, a long time ago. And strictly speaking, it's not a Born-Oppenheimer MD simulation, but something that is called Carparnello MD. And I'm not going into the details anymore of this method, because usually these days everyone is doing von Oppenheimer MD, but it's sort of very, very close to von Oppenheimer MD. And the reaction that I show here is a chemical reaction, and I actually should actually start here somewhere in the middle. So what you can see here is formamide. Does every one of you know how formamide looks like? Yes, so formamide, hydrogen, carbon, oxygen, right? A double bond to the oxygen. And then here you have an NH2 group, yeah? Okay, so you have double bond and then here single bond. And so this formamide, so this is basically a sort of a model for hydrolysis of a peptide bond, right? So this is a small model system, but it's so at that time I was interested in understanding the mechanism of cleavage of peptide bonds, which is important, like for degradation of proteins and things like this. And so this formamide here is in aqueous solution. So you can see here lots of water sort of swimming around, right? So lots of waters here. And that was actually a molecule in a box of 32 water molecules and then periodically replicated. You know what periodic boundary conditions are, right? So I don't show the periodic because it's so zoomed in. I don't show these periodic boxes there, but they are there. So it's a real sort of liquid condensed phase simulation. And in addition to that formamide molecule, there's also a hydroxide ion, okay, OH minus. And OH minus is rather well solvated in aqueous solution. But every now and then, and this is what I'm showing here, this OH minus attacks that carbon here and opens up that double bond, and then it forms a O minus and an OH. Okay, and this is what this movie is about. Basically, how this attack happens. That then is the first step of the breakage of that of the hydrolysis of that molecule. And okay, so let's just see. So this is okay. So this is again here this movie, and here you see this OH minus here, how it attacks that carbon atom. And so it's OH. So you see it's extremely dynamic. So the movie is maybe a couple of picoseconds long. And so it stays there, like here, but then basically it goes back. So it goes forth and back. And the interesting thing here is in this movie, I think, is that actually all the things that you, so this is von Oppenheimer molecular dynamics, right? So so what you see, all the things that you learn in organic chemistry or in chemistry are actually happening, which is at the beginning here. The molecule is planar, right? Because it has this double bond, a pi conjugated double bond. And as soon as the OH basically attacks and the double bond is gone, you see that the amino group, for instance, it is no longer planar. So it has typically the angle of a non-planar amino group. And here also the planarity is gone, right? So because this goes from sp2 to sp3, right, in the organic chemist language. But this is really what you can see, what comes out of this simulation. Now, so these simulations is just like interesting to watch these movies, but you can also actually calculate reaction rates, and you can actually, from this kind of calculation, you can calculate transition state free energies and rates, the number of times per second that these intermediates are formed. Okay, so there's lots going on, because you have to imagine that the OH minus is very nicely solvated in aqueous solution. And in order to be able to attack this molecule, it first has to strip off, get rid of its molecules that solvates it, right? So that requires quite a lot of free energy. And then this is partly then compensated by the energy that you get by the attack onto that molecule. Okay, so this is, let's say, an approximated Born-Oppenheimer molecular dynamics at around 300 Kelvin. And this is something, for instance, that you cannot really do with, well, you cannot do with this with classical force fields. You know, people are working on reactive force fields, but, you know, it's still not so clear basically how reliable they are. So this is one of the big advantages of ab initio. It allows you to do, you know, to do chemical reactions. All right. Any questions on this? No. So then I remove this and would like to talk again a little bit about theory. Particular, let's say, the StatMech aspect. So what can we actually do with these molecular dynamics? So you have already seen a few examples, but what you can actually do, you can calculate time averages, right? So you know, each observable that can be an energy, that can be a bond length, so that can be a dihedral or a torsion, an ionization potential or whatever, right? It will fluctuate in time, you know, depending on where the nuclei are. You get sort of a different instantaneous value of, let's say, you know, some structural parameter, let's say bond lengths, angles, or some energetic parameters. And this observable here, I just call very generally A as a function of t. Now you propagate your nuclei in time, so basically then also A of t will propagate in time. And so in general, an observable is just a function of all your phase space variables, R and P. Now R are just a collection of the nuclear coordinates, the same R that are used for the Schrödinger equation, and so it's exactly the same. P would be the momentum, right, of your nuclei. So that's the classical momentum because we're doing classical nuclear dynamics. As I said before, as you do molecular dynamics, these things will fluctuate in time, and you calculate the time average. So you just integrate that, or you take the average of that instantaneous quantity, you average it. And this is usually done by a discrete average, obviously, because we propagate the nuclei in a discrete fashion in, for instance, velocity. Again, here, obviously, here is the time step that we were talking about. Typically, half a femtoseconds, 1 femtosecond. I should say that often you see 2 femtoseconds. And the reason for this is obviously you always have to look at the fastest vibrations, right? The fastest vibrations in your system determine the time step. Now it can be sometimes in classical MD, you hold the hydrogen, the carbon hydrogen, or all the bonds with the hydrogen atoms, you fix them, and you don't let the hydrogens vibrate. Now the hydrogens, they have the highest frequency and require the smallest time step. Now if you remove of the vibrations with hydrogens inside, then you can, you know, then the next fastest would be then, let's say, if you don't have triple bonds, would be then CC double bonds or something like this, right? Then they have an oscillation time of 20 femtoseconds. So therefore, you can double your time step, and you can in classical MD often when you constrain the hydrogens, you have 2 femtoseconds time step. The nice thing of this, it just gives you twice as much long trajectories, right? So this is just an appendix of our discussion about the time step. Okay, so now the question is, Just remember now statistical mechanics, right? So in statistical mechanics, this is what we would like to do. We would like to calculate some, you know, some ensemble average, because in the end of the day, if we want to compare with the experiment that's done at a finer temperature, the experimental number will be an ensemble average. And so that means that if we want to, you know, predict any of these observables, we also have to calculate an ensemble average. Now the question is, how do the ensemble averages in statistical mechanics, like you know that NVE ensemble, NPT ensemble, NBT ensemble, you know all these, right? From statistical mechanics, yeah. So how does this, how do these things relate to the time averages that we calculate in molecular dynamics simulation? Is there a correspondence? Well, I hope there is. Otherwise, we will not be able to use molecular dynamics to calculate ensemble averages, which then can be compared to experiment. Okay. So, so this is why this comparison is important. So we know how to calculate time averages. Okay, that's not a big deal. Now, a few words on these ensembles in statistical mechanics. Now, you probably all know what an NVE ensemble is. So it's just a very large number of copies of one and the same system. Each one has the same particle number n, same constant volume v, and the same constant energy E. And so essentially the NVE ensemble is the collection of all the states in that classical phase space that have the same total energy E, right? And so this ensemble of state points, they form this NVE ensemble. Now, one of the fundamental assumptions of statistical mechanics is that the probability to find each member of this NVE ensemble is the same. Okay, so there is no sort of, you know, preference for one over the other. They have all the same energy, so the probability density for each of them is the same. So, so that means that here that the probability for one of these ensemble members is just that delta function. It's basically zero if this guy doesn't have the energy E, the target energy, and it peaks when it does have this ensemble energy. Obviously, you divide by the partition function in the NVE. So the partition function just counts the number of these states, and is given here by this last expression here. So it's just the integral over that delta function over the phase space. Okay, so this just really sort of counts the number of states that you have in your system. And just remember, what is actually our Hamiltonian here? Our Hamiltonian is nothing else than classical kinetic energy of all our nuclei that we propagate using plus this ER, right? That's the potential energy. And what's the potential energy? Where does this come from? Just making sure.
Still the potential.
Yeah, it's still the potential energy surface. So if you do ab initio MD, this is a DFT energy. If you do classical MD, this is just a force field energy, right? It's just the potential energy surface, depending on the nuclear positions R. Okay, here a few more. Okay, so that's this, right? So that's the StatMech definition of the NVE ensemble. And now the question is, how does this ensemble relate to the ensemble or the state points that we sample in molecular dynamics simulations? Okay, is this the same ensemble that we are sampling? And the answer to this is yes, if we assume that our system is ergodic. Okay, so the ensemble average now in the NVE ensemble is just you know, whatever observable you are interested in, A of RP times that density, this delta density rho times dr dp. And so the ergodic hypothesis assumes that if you do a MD simulation, right, that each state that has the same energy is visited the same number of times in an MD trajectory that is infinitely long. Okay, so the picture is the following. And now why is this actually true? Well, we know that you know, Newton's equation of motion, it preserves total energy, right? There is total energy doesn't get lost when you do Newton's equation of motion. So essentially, when we do MD simulation and we just draw this isosurface of the total energy in our phase space PR, what actually our MD simulation is doing is that it sort of, you know, has a sort of chaotic trajectory on that surface here, you know, but in the infinite time limit, each of these points on that surface are visited the same number of times. Okay, so that's the and this is what, you know, this is what the NVE ensemble is all about. So it's because the probability density should be the same for each of these points. Okay, so this is the ergodic hypothesis here. We calculate our time average from MD simulation and an infinite simulation time that approaches the ensemble average from statistical mechanics. Okay. Now it turns out that for most of the system that's actually true. So they behave in an ergodic way. What is problematic are systems like glasses, for instance, that where it's difficult to sort of sample the phase space in MD simulation, and so these can be non-ergodic, and in this case, this equality here breaks down. But so we're not considering this case here. So we always assume in MD simulation that this is actually true. Okay. Now, question. Now the NVE ensemble is quite nice, but is this actually what we should do if we compare to an experiment that is done at room temperature? Would this be?
No, because in real experiments we don't measure energy.
Yeah, usually, I mean, when you do an experiment in the lab, you usually do that at a given well-defined temperature
And pressure.
and you maintain that temperature by basically having a thermostat in your system, right? So whenever something is happening in your system that produces heat, then the heat will probably go into the heat bath. On the other hand, you know, like if something requires heat, it can take the heat from the heat bath, right? So so that maintains sort of energy flow, right? So so to complete the experiment, usually the relevant ensemble would be NVT or NVP, right? So you would have rather constant temperature rather than constant energy. Okay, so the question is now, how do we do this? And first, a few words on the canonical ensemble, or the NVT ensemble. Now here, again, you have a large copy of identical systems, and each one of them is connected to a heat bath, again, at temperature T, and you know, it's the system is allowed to sort of exchange energy with that heat bath. And so if you look then at all these members of these ensembles, of this ensemble, then you will see that, and you can actually sort of derive that using a maximization principle for the realization of a given state, is that the probability that the system is in a state with total energy H, as I call it here, is given by the Boltzmann distribution e to the minus beta h. Okay. And this beta here at the beginning in statistical mechanics is actually just a parameter in the end that doesn't have, like much more physical meaning than this. It's just then the comparison of this to the expressions from classical thermodynamics, is that then the meaning of that beta is equal to 1 over kT. Yeah. So this is then the meaning of this beta. Now, every point in phase space then has a probability of e to the minus beta h. And so since this is a probability density, you have to divide this by the partition function, so that when you integrate then that probability density over all phase space, the whole thing becomes 1. Yeah. So that defines your partition function, which is just the integral over your Boltzmann factors at each point in space, in phase space. Yeah. Okay. Now, again, if you would like to calculate the expectation value of an observable in that canonical ensemble, you just have to integrate over the phase space. Again, observable at a given point RP, you have to multiply it with the weight of that point that's given by that equation here, and calculate that integral. So the question is now, how can we simulate the NVT ensemble with classical molecular dynamics? That's the question, because classical molecular dynamics always conserves, or basically any molecular dynamics, if you don't do anything in addition, it doesn't conserve temperature. Well, temperature is actually not well defined in the ensemble. It only preserves total energy, right? This is not what we want here. Now, before I basically tell you about this more, I would like to talk a bit more now about temperature and kinetic energy. So, what is actually temperature? Any explanations? What is actually temperature? If I ask you the question, it's a bit of a philosophical question, I guess, but what is it? What does it measure, or what is it?
Just energy, really, isn't it? It's just a measure of energy.
Which
just
kind
measured
of energy?
from
Yeah.
Kelvin. I said kinetic energy, really.
Okay, very good. Okay, it's a measure for how much kinetic energy there is in my system. That's a very good answer. I have another question. Now, the kinetic energy, how do you define the kinetic energy?
Energy due to the motion of the atoms, so you can take into account vibration and motion of the molecule as a whole. Yeah.
Okay, so if you sort of remember in physics, so the kinetic energy of a classical point particle is given by mass times.
Yeah, like half mv squared.
Yeah, exactly. So half times the mass times v square. Now we like to use momenta, so it's p squared over 2m. It's the same. But during an MD trajectory, for instance, or so this would kinetic energy, it will sort of fluctuate, right? So you have to calculate the ensemble average of this, yeah, in order to get then a real number. So this is what we have done here in that equation in that slide. So we do take the the total kinetic energy of the system written here. N is the number of nuclei that you have in your system. And so, we know that this thing should be Boltzmann distributed. So let's calculate then the Boltzmann average of the kinetic energy of our system, and this is written down here. So these brackets in the end is averaging, Boltzmann averaging, and Boltzmann averaging means you integrate over phase space. You have your observable here. Your observable here is just the kinetic energy, and you multiply that observable with the Boltzmann weight. Okay, so which is e to the minus beta times the total kinetic energy, being kinetic energy plus the potential energy, as I said before, either from DFT or classical force, it doesn't matter. Yeah, and then obviously you have to divide by the partition sum here. Because you want to sum up all your weights, so that, you know, like it should be a weight. If you don't divide, then it wouldn't be a weight. Okay. If you look at this integral, how would you solve that? Any ideas? It's quite easy. Otherwise, I wouldn't ask. But I wouldn't. I don't know whether you see that. You know, at the end of the day, I get this number here. So that is very simple. But how do I get there? So the easiest one is let's first, so it's a highly dimensional integral, right? So it's 3n of these guys and 3n of those guys here. Okay. Now let's do the simple one first. Let's integrate over the atomic positions, dr, all the atomic positions of our system. So in the integrand here, which term depends only on the atomic positions?
Exponential?
Yeah, it's just this term here, okay? Good. So the exponential, you can write this sort of, you know how to write this. So this is e to the minus beta times the kinetic energy times e to the minus beta er, right? So e to the minus beta a plus b is e to the minus beta a times e to the minus beta b. Yeah. All right. Now that's in the count. And the denominator, you have the same thing, right? So you have the same term, e to the minus beta er times e to the minus beta kinetic energy, and then you integrate this over r. Yeah. So that means you have the same integrals, right? And the counter and then the denominator. Yeah, these are all Gaussian integrals. Well, this is not a Gaussian integral. It's just e to the minus beta r dr here and there, and so they cancel. Yeah. So it's the same integrals on both top and bottom, so they cancel. So the integral over r cancels. It's the same. Now, what about the integral over the momenta p? So that's a bit more difficult. So you have a p square. So this is that's Gaussian integral, right? You see that? No. Okay, e to the minus beta x square, like something like this. It's a Gaussian integral, right? It's a Gaussian integral multiplied with x square, with p square. I mean, the p is bold, but bold, don't worry about this. P square is just px square plus py square plus pz square. In the end of the day, you end up with this kind of integral here, which is analytically known. Integral over x squared times a Gaussian is square root pi over a times 1 over 2a. And here in the denominator, you would have also a Gaussian integral. But this is just a Gaussian integral, which is square root pi over A being beta. Okay, so that means, so the square root here, the denominator and the counter in the denominator, that vanishes again, this, and what you have left is 1 over 2A. So A in this case is beta, so it would be beta over 2, and that's 1 over 2 kt. Okay, and you get 1 over 2 kt for each degree of freedom, because this is a 3n dimensional integral. You have to multiply this with 3n, and that's why you get this final result, 3n over half kt. And this you have seen many times in classical thermodynamics, chemical thermodynamics. Okay, so you have a half of a kt of kinetic energy on average in your ensemble average in each degree of freedom. Yeah. Okay. So that's the meaning of the temperature, right? The temperature is proportional to the ensemble average of the kinetic energy. Now, NUSA thermostats. Now is the question: how can we use molecular dynamics to actually simulate the NVT ensemble? And just solving Newton's equation of motion doesn't bring us there, because it preserves total energy. So we have to change the equations, and that's what NUSA did. So in addition to the Newton's equation of motion, you are adding here a friction term. You see that? So the friction term here is this second term here on the right-hand side. And friction, you know, like from mechanics, right? So when do you have friction? As soon as the car moves, you have to overcome some friction term. And the friction force is proportional to the velocity. Okay. So the faster the car goes, the more friction you have to overcome. And this friction force, well, it's not a force in this case, is a friction acceleration or deceleration is the second term here. Okay, it's proportional to the velocity. And this psi, I'm not very good in this Greek alphabet. I think it's sort of looks similar to xi in the end. It's not xi, but it looks similar to it. Is the friction coefficient. Now, NUSA came up with this ingenious scheme where he says, okay, and this friction coefficient is not constant, but it also obeys an equation of motion. So the velocity, the change in time of the friction coefficient, is equal to the right-hand side of that equation. And the right-hand side of that equation that you can see is the instantaneous kinetic energy. Yeah, that's the first term, minus twice the average kinetic energy of my ensemble. Okay. Now, what you do then in thermostatic NUSA molecular dynamics is that you basically solve these two equations of motion simultaneously. Okay. And NUSA has shown if you do that, then your MD simulation samples the NVT ensemble. And obviously, since you have a friction term, the total energy of the system is no longer conserved. And what do you actually do in your MD? Remember, in the MD, in the NVE, you were just sampling one of these surfaces. But now you actually sample many of these surfaces, and in a way that is that obeys the Boltzmann weight of each of these points on these surfaces. Okay, so the weight of each point of the surfaces is proportional to e to the minus beta, the energy. Okay, and so this is the NUSA thermostat. what you can do is that you can calculate the time derivative of that modified Hamiltonian, and the result of that is this equation here. So over time, the total energy changes of the system changes proportional to that term here on the right-hand side. Now this friction parameter here is determined by that differential equation here. Okay, so that you also have to solve. Now, if, for instance, the friction coefficient is positive, then the total energy decreases. Obviously, everything is positive. This is negative. Total energy decreases. And that means you basically go down in energy, and then that's a cooling, right? An instantaneous cooling of the system. You're going down in total energy. If the xi parameter is negative, then the right-hand side is positive, and the total energy of your system increases, then you go up in energy. Okay, and that's the instantaneous heating process. And so again, if your dynamics with this Hamiltonian is ergodic, then Nuse has shown that these equations of motion that they preserve the Boltzmann ensemble. Okay, are there any questions? So this is how you can do NBT simulation with molecular dynamics. You just have to add this one friction term to Newton's equation. Okay. All right. Are there any other questions? As I said last time, if you have any questions, please feel free to drop me an email or something, or I'm also happy to do a call if you like. It can be, you know, like now or in a couple of weeks, doesn't matter. Okay.
Yeah, I have a question related to the thermostat.
Yep.
Because I have read that some simulators, they have like an equilibration state in order to achieve a temperature. And then they have like a production stage when they change to the MBE. But yeah, but which is the recommended way to compute properties at the end, in the MBT or in the MBE ensemble?
It depends which properties you're interested in. Let's say normally I would say you should do an NVT simulation. If you're interested in, let's say, thermodynamic observables, thermodynamic or kinetic observables that you then want to compare with experiment. If you want to calculate, let's say, if you're interested in the dynamics of the system, how the system, for instance, relaxes upon photoexcitation or something like this, and I would calculate this with an NV in an NVE ensemble, and often it's recommended if you want to calculate correlation functions to also do this in an NVE ensemble. So you know, it's a bit of a sort of sometimes a question that is not so clear cut. What I should also say is that if you go to very large systems, then the difference between NVE ensemble and NVT ensemble will become very small, because, you know, the larger the system, the smaller, relatively speaking, the fluctuations will become. And then if you have a very large system like you know, protein, hundreds of thousands of atoms or something like this, there will be not much of a difference between NVE and NVT simulations.
Okay, thank you.
All right, very good. So now we are at the end of this of these two lectures now. Thank you for attending. And yeah, if there are no further questions, then well, I say goodbye, and I hope that you enjoy the remaining lectures of this course.
Okay, thank you. Bye.
Bye-bye.
Thank you.
Bye.